We're here today to take a look at the graphs of motion for a simple harmonic oscillator. And then we're going to build on those graphs of motion, our position graph, our velocity graph, and our acceleration graph. And we'll introduce the idea of forces and energy and show how they all correlate to each other. So here is a simple harmonic oscillator in its equilibrium spot. And this thing will stay here unless somebody or something displaces it from its equilibrium point. And if somebody or something displaces this thing from its equilibrium point, then it will begin to oscillate up and down. And if it's a simple harmonic oscillator, we can assume that that happens and lasts forever without any frictional effects. Now, obviously, that's not what happens in real life. Objects become damped harmonic oscillators, meaning their amplitude will decrease over time and ultimately come to zero. But for us, we're going to think of these things as simple harmonic oscillators where this oscillation continues forever. So how do I make this thing a simple harmonic oscillator? I must displace it from the equilibrium spot. And as soon as I displace it from the equilibrium spot and set it free, this becomes a simple harmonic oscillator. You can see it goes below the equilibrium point and above the equilibrium point. And its motion can really, excuse me, be traced with a trigonometric, sinusoidal or cosine function, depending upon the phase and where you start the graph. All right. Now, the relationship between this stuff right here, this position graph, and velocity and acceleration is exactly what you would think, right? So acceleration is the rate of change of, or I'm sorry, velocity is the rate of change of position, and acceleration is the rate of change of velocity. And even though we're a non-calculus based course, some of you are familiar with these terms. Velocity is really the derivative of position, and acceleration is the derivative of velocity. So as we have this oscillator, what we're going to do here is we're going to trace out how the velocity function compares with the position and function, and again, how the acceleration function compares with the position function. So if I stop this thing again, it's difficult. This position graph starts at the equilibrium spot. Now, when I talk about things, I like to start from a displaced spot, because in reality, that's where your simple harmonic oscillation has to begin, in my mind. But really, it's just a function here of where we want to phase in and start the graph that we're looking for. So for me, I want to start this thing at the maximum positive displacement. So for us, let's call above the equilibrium spot positive. Let's call below the equilibrium spot negative. So if I displace this above the equilibrium spot and begin the oscillation, in reality, what have I done? I have begun this thing right here at what's referred to up here as letter C. Right? So the position function up here is the maximum positive number, which, oh, by the way, we could label as A, the amplitude, right? Because if I displace this 3 centimeters becomes the amplitude. When I let this thing go, again, it oscillates. Well, let's think about this. Every time it reaches the top again, it has to turn around and change directions. So every time this thing reaches the top, it is turning around and changing directions. Well, if it's turning around and changing directions, the velocity at that particular point has to be equal to 0. So if I freeze framed this up here at the top, it's turning around. So the velocity is 0. So anytime we have a peak up here for this position graph, we have a velocity equal to 0. So all of these C's on the graph correspond to a velocity that equals 0, because it's a turning point for the position graph. So now, all right, let's think about this. Let's go right down the line here, right? What's happening at each particular spot in this simple harmonic oscillation? Again, if I freeze frame this up here at the top, well, at the top, we have our maximum positive displacement. Well, the spring's job is to push this thing down. Now we're going to get to the force graph here in a second. We're going to kind of put the cart before the horse here. Look at it. F equals minus K times X. But F's cause accelerations. F equals ma. So if I want large accelerations, I have large forces. Not only do large accelerations cause large forces, but they cause them in the direction of the force, right? So in other words, if I exert a force on this water bottle in this direction, that's the direction the acceleration will be in. I'm not going to hit the water bottle this way and have it accelerate that way. When I hit the water bottle this way, it accelerates in that direction. So when I displace this oscillator in the positive direction, that negative creates a negative force, and the negative force creates a negative acceleration. And if I have a maximum x, I have a maximum force, and a maximum force creates a maximum acceleration. So anytime I have a positive maximum displacement, I have a positive negative acceleration. So all of these C spots are a maximum negative acceleration. All right, now look at it. What happens next on this position graph? If I displace this thing up here and I let this thing drop, well, it doesn't have any speed here. All of a sudden, it is gaining speed in the negative direction. Remember, down is negative. So we're gaining speed in the negative direction. Well, look at it. All of a sudden, I'm here at this equilibrium spot. Well, we learned yesterday that at this equilibrium spot, we have maximum kinetic energy. And we're going to get to those graphs. Well, maximum kinetic energy means maximum velocity, right? The other way to explain that is this. This thing is now compressed, so it's exerting a force downwards. That force is causing an acceleration. This thing accelerates. It's going faster in the negative direction. So once we reach this zero spot, we have reached maximum negative velocity. So every time this thing crosses the equilibrium spot on the way down, we have a maximum negative velocity. So all of these spots right after C and the equilibrium spot become maximum negative velocities. So all of these things right after the C's become maximum negative velocities. Well, what about the acceleration when this thing hits the equilibrium point? Well, look at it again. Acceleration is determined by force. Force is determined by x. So we have this kind of square logic here. If x is equal to 0, which is what happens here at B, then force is 0. And if the force is 0, then the acceleration also has to be 0. So every time we see this spot here at B, our acceleration graph is going to be equal to 0. So every time after this C, we have an acceleration equal to 0. Now you begin to see what's happening here. There are patterns. Well, then what happens here? So if this thing, simple harmonic oscillator, starts up here, hits the equilibrium, and then ultimately ends down here, displaced by the biggest amount in the negative, let's call that A right here. Anytime we have maximum negative displacement, hey, let's skip right down to the acceleration since we just came from there. Well, if a maximum positive displacement caused a maximum negative acceleration, then a maximum negative displacement will cause a maximum positive acceleration. How come? Again, if that's negative, negative of a negative gives us a positive force. Positive forces create positive accelerations. And big displacements create big forces, and big forces create big accelerations. So anytime we have the A here listed, right, we're right here. Anytime we have the A value, we are going to have a maximum positive acceleration. What happens to the velocity down here at the bottom? Well, again, it's a turning point. If I have this maximum negative displacement here, that's a turning point. Anytime we have a turning point, we have to have a velocity equal to 0. So just like all the high points had a velocity equal to 0, all the low points on our displacement graph will also have a 0 velocity. That's a turning point. And then finally, what happens here? We start here up at the top. We get the 0, we get to the minus. Now we come back here to a position of 0. So really, we have four. Yesterday we talked about 4 quadrants: top, equilibrium, bottom, back to the equilibrium spot. Now, if we're back to the equilibrium spot, now we are rising. So we know that the velocity has to be equal to a positive number. And if we're at our equilibrium spot again, we know that the velocity has to be maximum for 2 reasons. Number 1, this spring has been accelerating this thing all the way up to the equilibrium spot. And number 2, because all of the elastic potential energy from down here has been converted to kinetic energy. So again, anytime we had hit the 0 spot on the way down, we had our maximum negative velocity. Now we're hitting the 0 displacement on the way up. We have our maximum positive displacements, or velocities rather. So right before the C, we have our maximum positive velocities. Now look at what we have here, everybody, right? Look at what we've got for this velocity. We've got another trig function basically, and again, whether it's sine, cosine, is only determined by the phase, right? Like, look, I started at C because I think that's the easiest way for me to start, but look, let's just carry that thing on, right? And that makes sense. Again, anytime I have a position of 0, I've got my maximum velocities. So this thing, if I carry this on, this thing would be here. So what do I have here? I have a sine function here, and I have a cosine function here. And that makes sense from a derivative standpoint. The derivative of sine is cosine. Now, what do we got down here? Right? What am I doing here? I'm marking this thing here at the equilibrium spot on my way up. Well, the equilibrium spot is x equals 0. So if x equals 0, then the force equals 0. And if the force equals 0, then the acceleration equals 0. Again, we have this kind of square reasoning over here with these two equations. So again, anytime I have a 0 displacement right here, I still got to mark these things, I have a 0 acceleration. So anytime I have this 0 displacement, I have a 0 acceleration. So lo and behold here, what do we have? And what type of trig function is this thing? All right, this is a negative sine graph. And for those of you who are calculus people, the derivative of cosine is negative sine. So we have a relationship that is totally logical from a physics standpoint, and then from a math standpoint, it's also logical. So again, we've got all sorts of relationships we can build with respect to this. We've already built this acceleration relationship. The acceleration graph, again, because of this negative, if I've got a displacement, I negate that displacement. So my force is in the opposite direction as x. And if my force is in the opposite direction as x, my acceleration is in the opposite direction as x. So if this is a positive sine graph, then this thing becomes a negative sign graph. So my acceleration here and my force graph will match up, right? So again, we've already done this acceleration graph. Anytime position is equal to 0, my acceleration is equal to 0. Anytime I have a maximum positive displacement, I have a maximum negative acceleration, right? So anytime this thing is displaced up here, the spring wants to push it down. So I have a maximum negative acceleration. So at all of these C's, I have my maximum negative acceleration. And then vice versa, anytime I have this maximum negative displacement, I have my maximum positive accelerations. So I get a negative sine curve here for this. Right? Now again, we could have flip-flopped these two graphs, right? Because in reality, what causes accelerations? Well, forces cause accelerations. So we could have said, hey, like when I have this position graph here, if position's at its maximum positive displacement, I have a maximum negative force. We took it a step further in terms of doing our graphs because I wanted to do the velocities and the accelerations first. But in reality, if I have a maximum negative acceleration, the only way that happens is I have a maximum negative force. And if I have a maximum positive displacement, or acceleration rather, the only way that happens is if I have a maximum positive force. And if Hooke's law tells me that there is no force when x equals 0, if there's no force, then there's no acceleration. So our acceleration graph and our force graph are mirrors of each other for all the reasons that we've been saying already on this video. So if that's a sine graph, that's a negative sine graph, and that's a negative sine graph. How come? Because of the negative sign right there on Hooke's law. And then finally, what we can do is we can take a look at how the kinetic energy of this system varies with its position, and how elastic energy varies with its position / time, right? So since it's, we're graphing all this stuff as a function of time, but we're corresponding it to the position graph up here because that's easiest in my opinion. All right, so look at, as this thing is oscillating, we talked yesterday about how the types of energies vary. The total energy is always going to stay the same if it's a simple harmonic oscillator because we're in a conservation of energy situation. However, the type of energy and how much is in each of these buckets, this elastic energy bucket or this kinetic energy bucket, that will vary based on position. And then position, of course, varies with respect to speed. So look at, if kinetic energy is 1/2 mv squared, then we can correlate this kinetic energy to our velocity graph. Now, the easiest correlation occurs at the maxes and the mins, right? So when this thing's at the top and the bottom, at its maximum and its minimum, the speeds have to be 0. Well, if there is no speed, then an object has no kinetic energy. So anytime this velocity crosses the x-axis here, then that kinetic energy is going to be 0. And then likewise, when does this oscillator have the maximum kinetic energy? Well, it has the maximum kinetic energy when it is traveling fastest. When's it's traveling fastest? It's always traveling fastest at the equilibrium spot because the forces have had more time and distance to act on the object. And the other explanation is because all of the elastic potential energy from when the spring is compressed has been converted into kinetic energy. So anytime we're at this equilibrium spots, all of these B's right? We have a maximum value for our kinetic energy. Now look at kinetic energy, 1/2 mv squared. Sometimes this velocity is positive, sometimes it's negative, positive, negative, positive, negative. But no matter what the sign is on that velocity, if I square it, I'm always going to get a positive number. So my kinetic energy has to stay positive, so that anytime I have these maxes or mins, I'm just going to have a maximum positive kinetic energy. So we end up with a graph that looks like this. And the elastic potential energy has got the same type of setup, same type of logic. Look at elastic potential energy is dependent upon displacement. So anytime this displacement is equal to 0, which is all of the B's, anytime the displacement is equal to 0, that elastic potential energy is also equal to 0. And anytime the position is as great positive, right? Up here, we got our most energy, elastic energy, because we're compressing this spring. Down here, we have the most elastic potential energy because we're stretching the spring the most. So at the tops and bottoms of this oscillation, here and here, we're going to have our maximum elastic potential energies. Now again, whether that position is a large positive number or a large negative number, I got to square that x. And if I square that x, I'm always going to end up with a large positive number. So my graph for elastic potential energy is going to look like this. And if you pay attention, right, since the total energy has to stay the same in this simple harmonic motion, anytime kinetic energy is large, we've got an elastic of 0. And anytime the elastic energy is large, we have a kinetic energy that's equal to 0. And that lends itself to a conservation of energy situation. Now, obviously, if we're talking about, in here, we've got some kinetic and some potential, and then those two numbers would add up to the same amount as well. So there's all of our relationships, or maybe not all of our relationships, but an awful lot of relationships that exist in this simple harmonic oscillator. So again, it looks, this thing's just going up and down, up and down, up and down, but it's a great illustration of all the stuff in physics that we've talked about so far.